Today is week 5, day 2 of our summer workshop in quantum sciences. And we're very happy today to have demonstrations later in the session by Henning Weier from qutools, who will show in real time an experiment that violates the Bell inequalities, which is one of the biggest deals in all of quantum physics. And it's really cool that this can be demonstrated in real time on a Zoom call. That certainly wasn't possible even 5 or 10 years ago. So let me review a little bit. We talked last time about the fact that if we analyze correlation experiments using classical common sense logic rules, that we can make predictions that have nothing to do with quantum physics. They're simply predictions about any possible experiment that could be done on any physical system. And the idea is to look for correlations between measurements on two different objects or two different sets of objects. And so I'd like to start today with just reminding people how to calculate a correlation. So this is a question from the pre-class questions from last Monday. So I'd like to go ahead and run this poll, launch the poll, and I'd just like you to write down on a piece of paper. You might have to write this out on paper to get the answer. So remember how you do this is you multiply this number times this number, and then you add that to the product of this number times this number, and then you keep doing that, and then you divide by 10 at the end. Okay, we have 6 replies, so I will end the poll. And I think people have the right idea, but there's a little bit of misconception there. If you multiply these all correctly, notice the minus signs, and when you add those products up, you get -2. Some people did and got +2, but I think you understand the idea here. And then when you divide by 10, you get -2 divided by 10, so it's -0.2. Okay, so that number is close to 0, you could say. If it were exactly 0, we would say, well, if we had thousands of samples instead of only 10 samples, and if the number came out very close to 0 within the margin of error, which has to do with how large your sample size is, like in an election, if your answer were 0 within the margin of error, you would say, well, those variables look like they're uncorrelated. If the number were, say, -0.5, and that was more precise than the margin of error, then you would say that those two variables are likely anti-correlated. If the result were +0.5, you would say they were probably positively correlated. Okay, so with that little math review, let's go back and just repeat quickly the case of tossing 2 coins. So Alice tosses a coin and gets a value C. Bob tosses a coin, gets the value Bob C. And this is a list here of some random numbers that I generated. And as we know, the correlation is the average of the product of those 2 values for each run or trial. And then we average it. So here we get approximately 0. And I've, I assume we have many samples here, so it's 0 within the margin of error. So the correlation we're going to say is approximately 0. Whereas over here, we have a case where notice that Alice and Bob always get exactly the same result, +1 or -1 together. And so in this case, because the product of -1 times -1 is +1, all of them are +1. So the average is +1, so the correlation is +1. So we say that these are positively correlated. If this were -1, we would say they were anti-correlated. Okay, now we talked about the classical model, which I defined in terms of 2 dancers. The two dancers perform in separate halls, and Alice observes one of them and records the leg position that she sees, AL, which she denotes plus or minus 1. And she also records the arm position. Alice sees the arm plus or minus 1. Bob does the same thing. Bob sees the dancer's leg, and Bob sees the dancer's arm. So initially we assume that they can record both the arm position and the leg position once every 10 seconds and write those down in a list. And then they will get together after the performance and compare the lists and calculate the correlations. Okay, so here's an example. No, this is not an example. This is the exhaustive, complete list of all possible combinations of the 4 measurements that Alice and Bob would observe. And there's only 16 possible different combinations listed here in this chart. And then for each one of those 16 combinations, I've calculated these products. And then from those products, I have done the 2 things. I've added across to get the sum variable. And I've also defined this curious quantity called Q, which is the plus, 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 minus combination. And the theorem that we saw last time, just by construction, you can see it in this table. There's no mathematics needed other than what's in this table. It shows that no matter what happens, if you record all the possible values, the Q cannot be greater than 2. Therefore, the average of all the Qs over different trials cannot be greater than 2, regardless of what distribution of these 16 possible combinations are actually observed. Okay. Now, the reason we focus on this Q quantity is because it turns out that by measuring the average of Q, we can distinguish between classical and quantum physics, which is a very remarkable statement that nobody knew until about the 1960s when John Bell pointed this out. Einstein would have been really fascinated by this result, but unfortunately he passed away before then. So here's a simulation that I did showing that if I randomly block out 2 of the 4 of the possible observations on each trial, then you can only calculate one of the products for each trial. So here's a random simulation showing that product, this product, that product, and that product. So now in order to calculate the average of Q, we have to average the numbers down. We get, in this case, 0.25. That is the average of Alice arm, Bob arm, which is the correlation of Alice's observations of arms and Bob's observation of arms. So the correlation of those 2 quantities is 0.25. And then I simulated the other cases, the other 3 cases. And to get the average of Q, we just have to add these numbers, because here's the expression for average Q. It's the average of this product plus the average of that product plus the average of that product minus the average of that product. So to get the averages, we have to sum them up and divide by the number of samples. But to get the average Q, we just sum the averages, because that's how average Q is defined. In this case, it's a random example. It turns out to be 0.167. Okay. Now, average of Q is not affected if the data set is large and the sampling is fair, namely random. So those which we observe and those which we block out are fairly sampled and randomly sampled. Under that assumption, we would think that average Q should always be less than 2. Okay, so here's a poll question. Okay, we have 5 responses. So in that poll, most people said no, which is correct. As I just said on the previous slide, if the quantities to be measured, namely the 2 out of these 4 quantities to be measured on each trial, are chosen at random by Alice and Bob or by some other mechanism, and they're chosen uniformly, randomly, and fairly, then, and you have a large data set, then it's not possible to get Q greater than 2. That is essentially the most important statement of this entire session. And here it is in a blue box, okay? For any data set, okay, if Alice has 2 variables and Bob has 2 variables, and they're combined in this way and sampled many times, fairly and randomly on the 2 sides, and then this correlation is measured by averaging this quantity Q under the assumption of inherent properties or instructions and fair sampling of measurement settings. No matter what state is prepared and no conspiracies or rigging, the average of Q cannot be greater than 2. This is the famous Bell inequality. There's some assumptions there, which we'll discuss in detail, right? I see a question popped up here, perhaps. Is there a mathematical proof for Bell's method of determining the average of Q? Or is it coincidental? The method for determining Q, there's 2 aspects to that. One is, why did Bell define Q in this particular way? Why is there a minus sign here? Okay, there's many different ways you could combine these correlations to define some different quantity. Bell checked all of them and found out that this is the best one for distinguishing all classical predictions from other kind of predictions, for example, quantum predictions. It's the best one. And then as far as calculating the average of Q, what I just showed on the previous table is simply elementary statistics, and there's no other way to do it. It's just common statistics, which has been known for hundreds of years. And okay, so now we're going to have another poll question. Good. So we have 5 responders and actually 6 responders, and 5 of those responders indicated the answer to be yes, and that is correct. And it's really a matter of understanding what I mean by chosen in a selective way. So rather than using like a coin toss for Alice to decide whether to measure arm or leg, and Bob tosses a coin to decide whether to observe Bob arm or leg, that would be on the previous slide, which I call it random, uniform, and fair sampling. Each one uses a fair coin toss. But now, if we have some very tricky selective way, then you can create almost anything you want. And here I've taken the previous data and I've simply selected by hand those combinations of here's leg, leg, here's arm, arm, here's leg, arm, such that I would get all these numbers to be +1 and all these numbers to be -1. I can do that because, you know, I know what all these numbers are over here, and I've selected out the ones that I want by a tricky method, which I'm not telling you about. It would be some unknown physical mechanism, a little demon in the physics that's doing that for you. So then in this example, what is the average of Q? There's no poll question, but just work it out in your head. Look at the bottom row here. These are the averages of the columns. Therefore, these are the correlations. Those are the quantities that appear in this formula. So I'll give you 20 seconds. Okay. Okay, good. So we see the answer is 4 because it's 1 + 1 + 1 - -1. Okay, so that's 4. Well, 4 is obviously greater than 2. So if you do some experiment or somebody does it and they get a result of 4, you know that it could not have been determined by fair sampling of Bob's and Alice's choice of measurements. There must have been something else going on. Okay, and this says if Q is measured to be greater than 2, there must be some kind of rigging going on, like a rigged sampling. Like when companies go out to do polling for presidential elections, right? It's always a concern that are they fairly sampling the population, or are they just going to specific populations in order to skew the results to the way they want the poll to come out. So this would be an example of skewing the results of a poll. The question is, can physics and can nature skew these quantum measurements in some strange way? So the experiment that Henning will show is there's a source of photons, which of course is our favorite source. Blue light comes in from a laser to a crystal, and a blue photon is annihilated, producing a pair of red photons, which go off in different directions. Then they go through calcite crystal analyzers, although Henning actually uses polarizers. So in Henning's case, only one of these beams is passed, and the other one is blocked by absorption in the polarizer. And then there is a detector here that Henning has, and he gets clicks. And then he can rotate this crystal. So instead of being HV, it's DA, or it's 25.5. It can be different angles, rotating this polarizer, and then seeing how much comes out into this detector. On Alice's side, there's also a polarizer, which can be rotated, and a detector. And so then we look for coincidences between the detector located here on Alice's side and clicks detected on Bob's side here. And then we look at those coincidences, and then we vary the angles between these two crystals. And if this crystal or polarizer is set to HV, we say Bob has chosen to measure the HV property of this photon. If this polarizer or crystal is rotated to DA, we say that Bob has chosen to measure the DA property of this photon. And of course, in reality, I shouldn't use the word properties, should I? That's the classical way of thinking. That's like the arm and leg, where we know there's a value to the property, whether we measure it or not. But with photons, that's not necessarily the case. So I shouldn't say measuring the property. I should just say we rotate this analyzer to a certain angle, and we see if we get a click or no click. That's really all we can do. So do we expect correlations between Bob and Alice's measurement outcomes? Well, it depends on the quantum state. If this source of the photons is made in a joint quantum state so that the photons or polarizations are uncorrelated, then there's no correlations. But if the state is designed in a special way, which Henning can do, in order to make correlations between the state here and the state here, or I should really say that the global state of these two photons is in a correlated state, then there are correlations that are observed at the two detectors. So to compute these correlations, we'll denote, if it clicks here or not, we call that a plus or minus 1. And if it clicks here or not, we call it a plus or minus 1. Ideally, we'd have two detectors. Henning would have two detectors, one here and one here. This click would be a plus 1, this click would be a minus 1. But it turns out it's sufficient to only have one detector and you can get the same results. So I call this a magic trick. You'll see why. Here's the setup. Alice measures either variable called W, and again, I imagine there are two detectors here. So this, talking in those terms. If this analyzer is oriented HV, as I've shown in the picture here, then the variable that we're measuring is called W. Namely, if the photon goes to this detector, it says W is minus 1. If the photon goes to this detector, we say W is plus 1. Okay. Alternatively, Alice can decide by some random scheme, say flipping a coin, whether to keep her crystal oriented this way or rotate the crystal by 45 degrees, 0 or 45. If she does rotate this crystal by 45, then she's measuring the photon in the DA scheme. And then we assign the variable, call it X. If this detector clicks, X is plus 1. If this detector clicks, X is minus 1, or vice versa. So Bob does the same thing. He can either have the HV orientation, or, sorry, this is not HV. this one, well, actually, they can do anything. But I think Henning is going to stick with these two schemes here, as far as I recall. So what Bob does is he has two possible schemes. One of them is the 45 scheme, and that's HV. But in the 45 degree, no, I'm wrong. Sorry, start over. Bob has two possible schemes. One is the 22.5 degree scheme. And there's two detectors, and this variable is called y prime. And y prime is either plus or minus 1, depending on which detector clicks. Or he rotates an additional angle so that this is now 67.5. And I've shown these little arrows over here. So this is called the D prime A prime scheme, and this one here is called the H prime V prime scheme, because it's just like you took this whole apparatus and tilted it or rotated it by 22.5, including Bob. And so he would now define, you know, this axis as the vertical and the perpendicular one as the horizontal. So that's why I call it H prime and V prime. But really, in the experiment, all you have to know is the crystal is set at a certain angle and a variable is measured. It's called y prime. If you rotate the crystal to a different angle, the new variable that's measured is called z prime. So you see the analysis of this experiment from the classical point of view doesn't matter at all what the setup is. So you're probably getting really confused about the polarizations and what the primes mean. It turns out it doesn't matter. This whole thing could be in a black box, and there could be somebody inside this black box telling Alice, okay, I've set your analyzer to a certain scheme. And now make your measurements. And then the person could say, now I've set it to the other scheme. And now I've set it back to the original scheme. So it doesn't even matter what the schemes are, because Bell's inequality proof that we already went through today in detail proves that no matter what these four measurements are, the Q average that is measured from any experiment can never be greater than 2, under the assumptions of inherent properties and some other common sense assumptions, okay? And just to emphasize, on a given run, Alice and Bob can measure only one property each. That's just the setup. Okay, so we might get back to this later. This just shows in a little more detail the polarization schemes. D is a linear combination of V and H. A is a different combination of V and H. What I call D prime is this one, which is a 0.38 H and 0.92 V. And what I call A prime is minus 0.92 H plus 0.38 V. Okay, so that's the point. Again, Alice can choose one of these two measurement schemes. Bob can choose one of these other measurement schemes. Okay, so again, just to state it one more time, the Bell inequality should hold for photon polarization under these assumptions: no conspiracies, rigging, and the existence of inherent properties or instructions. Okay, so this shows what a typical run would look like if Henning could measure all four of these variables simultaneously, which we know is impossible in quantum physics because of the way photon polarization works. But the way Bell's proof works is you imagine you could measure all four of these polarization quantities simultaneously, and then you would run a simulation and you would get a bunch of -2s and +2s over here for the Q value, which is calculated by knowing all four of these quantities on each run, which is impossible, okay? But then you would get, you get average of 2 cannot be greater than 2. But then, just to repeat the argument one more time before the experiment, if you randomly and fairly sample these numbers so that you're only looking at 2 of these 4 quantities at a given trial, and you have a large sample, large enough that your measurements are within the margin of error, and then you calculate the average of Q by averaging down on the 4 columns and then summing over on horizontal direction to get the average of Q, this table still shows that under those conditions, there's no way average of Q can be greater than 2. Under those assumptions about the way the universe works, which seems very common sense. Okay, so this is the experiment that Henning will do, except he only has one detector on both sides, and Alice can have 2 possible choices to measure W or X, and Bob can have 2 possible choices to measure Y prime or Z prime. Henning might use different names for those 4 variables, I don't recall, but I will now turn that over to Henning. So please.
Thanks. Good. So, okay, we will just say we've already looked into our source a little bit in the first session, and we've shown there that we had produced heralded single photons. Then we've done some QKD experiment, and last time we've looked into interference with these single photons. And today, as Professor Raymer has already told us, we're going to go look into the Bell inequality. So I've taken a few images from Professor Raymer's slide to connect there again, and this is what he's just shown us. How we could do this if we had calcite crystals on each side, right? And then we have these 4 settings W, X on Alice sides and Y and Z on Bob's side. I have not denoted them with the prime now, but as has been said, if you find, or let's say for any of these sets, independent of what polarizations they actually denote, this formula should never be greater than 2, right? And this is what we're going to test. So we're going from the calcite idea to the polarizer idea. So this is not very difficult, actually. The only thing that basically changes is that you have sort of, for this one value that you have in the calcite crystal case, so for the W setting, now you have sort of like a W plus where you can only detect the +1, and the W minus where you can only detect the -1. And that's the same for all these settings. So you always have to set sort of make one more decision what you want to detect, and then you either detect something or you don't. But you don't detect sort of the other way, because as Professor Raymer has just told you, it can be mimicked as a calcite crystal where one path is blocked afterwards, or there's simply no detector in this one path. Right, so this is what we have to keep in mind, but I think that's going to be quite easy to do. And then we said that if we have perfect anti-correlations, all these values will always, the product of all these values will always be -1, and this also holds for the averages, right? And if we don't have correlations, because, for example, we haven't chosen these settings very well, or these schemes very well, then we don't see any correlation. And no correlation at all would mean something like 0 or close to 0. And then we had, Professor Raymer had introduced this dancer idea, which I found very interesting. And so there we always have one part that Bob is looking at, and we can have leg up, leg down, or arm up, arm down, and Alice is also looking at the second dancer, and there she has the same possibilities, or let's say measurement outcomes. And then this was the formula that we've seen. So we take the averages of some of these correlations, let's say, and add most of them and subtract one of them, and then we've seen that the average of this curious quantum number, whatever, has always to be, or it can't be greater than 2, right? And if it does, then we can say either it's rigged or something else is happening that's not somehow compatible with our classical idea of these dancers, right? So how do we get from this classical average Q to our quantum average Q, or the measured average Q that we are now going to measure with the polarizations of photon pairs, and this is what it looks like. So we basically have this a Alice arm times Bob arm can be translated into something which we could also call X now, right? This was called X, for example, or W, for example. So these belong to these polarization rotations that we've already also seen before, like 0 degrees is H, and 67.5 degrees is already a little bit closer to vertical. So that was like vertical prime, for example. And then we have the same with 45 degrees, that's diagonal, and 22.5, that's basically in between H and diagonal. So you will see that always the first one will be in HV or diagonal and diagonal, and the second one will be rotated by 22.5 degrees. And this is just it's not a random choice of how you choose these W, X, Y, and Z. But it turns out this is a sort of a good choice to do this. But you could choose every other setting, but you might not get the result that we will get later. Right. So as I said, this is a good choice. So let's start measuring actually, and I will briefly have you see the setup, but this has not changed at all. So it's a bit darker today, but this is the setup, as you can see. And now let's go to this. Right. So now we have a different setup way or a different view of the setup. You can see this, you've seen before too, right? You see a sort of closer look at the polarizers, and you see this is again the screen of the device. This is not doing anything at the moment, so you don't have to worry about that. And you see some, I hope you can see this Excel sheet that I have here, and I will put in the numbers that we're going to measure. And I'm going to measure these coincidence rates, which is basically what we've seen before. It's sort of the sum of all these plus and minus ones. But in this case, since we always have clicks and we count clicks, we basically just take the sum of this, and this is this coincidence count rate. And that's exactly what we're going to see on the screen. So I just have to put in these count rates in this Excel sheet. And before that, I'll have to set the polarizers in the right way. Right. So here you can see the first polarizer. This is, let's say, Alice's polarizer. This is going to go to 0 degrees. 0 degrees means H. And Bob's polarizer is going to go to 22.5 degrees. And then we're going to take the measurement. So you can see I hope you can see in this case that we have here in the upper left corner, it means H for Alice's polarizer, 22.5 for Bob's polarizer. And I've clicked on that, and it's already like set like that. And you can see that on the small camera image. And now I'm going to let it count for 10 seconds. And the value that's going to come out of this we'll put into the Excel sheet. Right, so this has changed, right? This is 2,505, and I will put this into this Excel sheet now. Right, that, and then we're going to go, the next one is 0, that means H again, and 112.5 degrees. So this is this, and the polarizers have changed. Let me just go back to show you. You can have a look at the small arrows on the polarizers. So if I change them, you can see them move. And now I'm going to count for 10 seconds again. And when this number changed, I will put it into the second line of this. So this is obviously a higher number. Right, we don't know what that means yet, but that has changed. So the next one is 90, that's V, and 22.5, so this one, let it count. Right, 76, that's not a very high number. And now we go to V and 112.5, and let it count again. $177. Now we're going to go 45 degrees. This is denoted here as plus, and 22.5 degrees. So that's that one. Let it count. One, 6, 5. And now we're here. Plus, oh, sorry, we're, yeah, that was the right one. V, that's 90 degrees and 112.5. No, that wasn't the right one. So 45 and so 45 is plus and 112.5. That was the right one. Sorry. I have an automated version of this that we're going to take later, so it's not going to be so difficult for me, at least. Okay, 7045. And now we're at minus 45 degrees and 22.5. So we're here. We're gonna see if I mess it up. It's gonna show on this. Okay, that's 1, 2, 3, 2, and now we're at minus and 100. Okay, we're close to half time here, so it's not going to take forever. Okay, 8817, and now we're again at H and 67.5 degrees. This one. Okay, 15327. H and 175 degrees. So it's good that it's morning where you are and not late at night. 3279. And now we have V and 67.5 degrees. That's this one. $167. And we have V and 157. This one. If somebody sees that I'm messing up, please let me know. Okay, 161. Now we have plus 45, 67.5. Plus 4,500. Now we have minus and 67.5. $7,902 and minus, and that should be the last one. 2, 1, 1, 3. Okay, so our average Q is 1.46. Now that's a bit disappointing, right? So let's go back to our slides. Okay, so we see that this value is not as high as we wanted it to, right? So it's 1.45. What does that, or 1.46 actually was. So what does that mean? We have said that if this value is higher than greater than 2, then we can sort of exclude, or we can sort of conclude that something strange is going on. So what does that mean if the value is lower than 0, lower than 2, sorry. Does that mean that we can say, you know, this is definitely not rigged, or there's nothing special going on? And this is something I want you to think about for a few seconds. And the next thing is, well, where could this come from? I mean, what did I do something wrong, or, you know, where could this come from? And I will give you a few seconds to think about this. Okay, so the first thing is, if we say that we know that, you know, something's strange or something happens if something's greater than 2, then if it's not greater than 2, then the logic tells us that we don't, you know, we can't say that something else is going on. So we simply didn't, you know, nothing much has come out from this experiment. And what Professor Raymer also told you why this could happen is if we this average Q is state dependent. So if we put in a let's say not the Bell state, but sort of something between something correlated and uncorrelated, maybe you see that the correlation is not 0. So if we had something completely uncorrelated, we would have expected something close to 0. That's not the case either. So what happened is that I didn't put in the Bell state at the moment. So I will change this now, and we will see what happens if the Bell state is in there.
So Henning, you could just comment, as you say on the slide, that you put in the HH state.
Yes. So both photons had been horizontally polarized.
Yes, which Henning can control by the settings of his crystal, but it turns out that's not the Bell state. So now he's going to reset the source, so it actually does produce the Bell state.
Exactly. So I can show you what I will do. I have something in here, some optical element that controls the state that actually is produced. And I have changed the setting of this now so that we will actually produce the Bell state now. And so that you don't have to suffer for such a long time again. And then I cannot make so many mistakes. I'm going to get rid of this, and we're going to do this in a little bit quicker way. So let the computer do all these settings and count it, and also calculate this value that we have. So let me get to this. Where are we? Okay. So I'm going to give you this view again, but the Excel sheet is not very important anymore. You see the value from the old measurement, but you can now see in the upper right-hand corner the screen again, and in the lower right-hand corner you will see what happens with the polarizers. So I will start it, and you will see that it'll be. I'm only counting for a second now, so that this goes a little bit faster. And also you can see that the values are appearing already, the count rates are appearing sort of automated. And when this is finished in a few seconds, we will see what the experiment will look like. Right, so here you have the average Q value, right? I didn't note it as average, but this is the average Q value. And now alas, we've seen that this is greater than 2, which is what we really wanted to see, right? And I can do, so now you can see this has been calculated to a lot of digits, so 2.613. And if I simply do this again, you will see something a little bit different, of course, because all these experiments will not always show exactly the same number. And we will get into that a little bit more. So right. So this is what we see now. So before it was 2.6 something, now it's 2.5 something, and you can already see that there seems to be a little bit of a statistical fluctuation, and this is actually what the next value shows. So this is like the margin of error that Professor Raymer has already talked about, and he will explain maybe in a little more detail later what this means. So this means that there is some error on this, and I can make this error sort of smaller if we take let me check, if we do the experiment for a little bit longer time, for example. Now, before we had taken 10 seconds for each measurement. Now we're taking, then in between it was like 1 second per measurement. And now we're taking 2 seconds per measurement. And again, we have these 16 values. And from these 16 values, we simply correlate, or now the computer does compute this average Q value, right? Right. So now you see that the value is still a lot greater than 2, and this margin of error value has become a little smaller, and it could become even smaller if we took a longer time to measure, which we're not going to do now. So let's get quickly back to these slides. So we've seen that this average Q value is greater than 2. So this means that we have one of these, at least to a high degree, a correlated, or in this case, it's actually an anti-correlated state, which is the state that Professor Raymer has introduced before. And we've also looked at what happens if we do this again, and there's some sort of error on the measurement, but we can also calculate how large this error is. I haven't shown you how this works exactly, but right. So the whole question was, are there these inherent instructions, right? So can we say that we can exclude maybe these inherent instructions? Because as Professor Raymer has said, Bell's inequality says that if this value has to be smaller or equal to 2, if these inherent instructions are assumed, and some other things that are also assumed, right? Like this fair sampling, for example. And right. So inherent instructions, it looks like it doesn't work with inherent instructions. So this is something that at least in our everyday life is a little bit strange. And then there was the question, could it be rigged? So that was like, if these fair sampling assumptions, for example, do not hold. And this is something that we cannot show with this very simple experiment, but there have been a lot of experiments that have looked into this. If you want to look this up, this is subsumized under the name loopholes. And there have been quite a lot of very careful experiments that have tried to exclude a lot of these loopholes already. So it seems that probably it's not a problem of the experiment itself. It seems to be that these inherent instructions actually do not exist. Right, and with this, I think that's it for today. Thank you.
Okay, thank you very much, Henning. That was fantastic. I'm going to reshare my screen now. and make a few comments. Well, the first comment I'd like to make is on the assumption that Henning did the experiment correctly, which I have great faith in, and that we understand the Bell inequalities and how simple it was to prove that without even using mathematics. The fact that average of Q was shown to be greater than 2 within the margin of error is, if you really understand it, well, the more you think about it, the more astounding you should find this result. Let's get back to that. But first, let me just mention a little bit about the margin of error argument. So I just grabbed this slide from Wikipedia, and just remind you that margin of error is a statistic expressing the amount of random sampling error in the results of a survey. Okay, the larger the margin of error, the less confidence one should have that the poll result would reflect the result of a survey of the entire population. So this curve here is the probability, as it says down here, the probability of polls of different sizes. So if you run a poll with a fairly small number of samples, like here's 96 samples only. So you go out and you ask, 96 people to give me a yes or no answer on a question. And then you report the result. There's a very broad distribution, which means you're not really sure if the given answer is representative of a much larger population. So then you go back to that same population, which might have 1 million people in it, and now you sample, say, 384 people. And that means now the margin of error has been reduced from 10% down to 5%. And so the distribution of your confidence or your probability that the answer is valid becomes narrower. And then if you sample 1,000 people, the margin of error comes down to 3%. Okay, so in the modern day experiments, well, even the one that Henning did, the margin of error was very, very small. It was much less than 1%. We won't bore you with the details, but he did show a number on the screen that was indicating how large the margin of error is. And it was much less than 1%. In fact, I think it was much less than 0.01%, 1/100%, which would mean that the probability that the results came out the way it did, just by sheer coincidence, is 1 part in 10,000. And Henning just did that experiment 3 times, right? Now, if Henning had 20 more minutes to run it longer, he could get that margin of error down to 10 to the -6. And then other research groups around the world have done it so well that the margin of error, I think, was something like 10 to the -50. So the probability, and the results were still that Q was much greater than 2. So the probability in those experiments that this result came purely from statistical sampling error or fluctuations is 1 part in 10 to the 50. So essentially it's 0. So we really do believe that the experiments are statistically significant. That's an important point. Here's the first experiment that was done of this sort. This was done, actually, this is not a picture of the first one, but the first one was done by John Clauser, a professor at Berkeley in 1974. And most people at that time didn't understand why he was doing this experiment. They thought it was kind of pointless. In 1982, a French physicist in Paris, Alain Aspect, improved the experiment. And he also got this result. He got it was greater than 2.7 or 2.8. And here's the apparatus. This is a screenshot from his original paper in 1982. It's in French, of course. Here's the source. Here are the polarizers. Here's a lens to collect the light coming from the source in 2 directions. Here's the polarizer. No, this is just a frequency filter. Ignore that. This is the collection optics. This is the polarizer over here. And it's a calcite crystal. So it sends the the photon coming this direction, either to this detector or this detector. And likewise on this side, calcite crystal, 2 detectors. And then here is the computer of the photon that calculates the coincidences. And you get the result. It was around 2.8, much greater than 2. And so here's a cartoon of John Clauser, who says, this seems to imply inherent instructions for photons do not exist. Now, I saw John Clauser a few years ago at a conference, and he gave a talk, and he made the interesting comment. He said he did that experiment in 1974 in order to prove that inherent instruction sets do exist. He believed in kind of realism, reality, that each photon was a thing and it had certain properties, and we're going to measure those properties. And so he adopted the viewpoint that probably something was wrong with quantum mechanics, and he was going to verify and prove that the classical probability theory and common sense is correct. And he was really surprised when he proved the opposite, that the classical probability theory actually fails. Okay, and then so here's a picture of Alain Aspect, who is here. I put the words of Alice in Wonderland into his mouth, curiouser and curiouser. I think there might be a question in the chat window. The question is, would the result be different if you move the source slight off the center between 2 polarizers? The answer is no. The polarizers don't have to be aligned along a particular axis. Well, what I mean is the beam propagation axis, the axis along which the light travels. The beam, in fact, you saw in my apparatus here in my basement lab when I was sending those laser beams through the crystals. I didn't show it, but if I move those crystals slightly off axis, it doesn't affect the result. Of course, what does affect the result is if you rotate the crystal in the transverse direction, so you're analyzing a different polarization scheme. And Henning showed those motorized rotators that were rotating the polarizers to different angles. And so to get this result, you have to have the right state of the photons, which is the Bell state, and we'll talk about that later, what it is. And then you also have to have the right combination of polarizer analyzer schemes. So it seems like a fairly tortuous argument, and that's why it took 100 years for people to figure it out. But once it's actually done, Henning did it, it works. You get Q average is 2.5 in his case. And to emphasize that point, the entire apparatus that Henning was using could have been in a black box, and he could have even explained nothing about what he was doing. As long as the 2 detectors were outside the box and the analyzer crystals were outside the box, and the source is even the analyzers could be inside the box, and there could be an operator inside the box controlling the analyzers. And Alice could just tell the operator, okay, rotate, or choose my measurement scheme to be the first possibility. And now choose my measurement scheme to be the second possibility. And Bob could do the same thing and instruct his scheme operator to choose one of the other. And you go through all the combinations, and Alice and Bob did not have to know what's in the box and what the measurement schemes actually correspond to physically. If they get Q averages greater than 2, they know that that experiment, whatever it happened to be, is violating classical probability theory under the standard assumptions. Okay. So let's discuss that in more detail here. So these 2-part experiments seem to rule out the possibility that nature follows inherent instructions. I say seems to, because there could be sneaky ways out of this conclusion. And Henning mentioned the word loopholes. So, logical arguments can have loopholes or workarounds. So it seems to be that if you look at the table of properties, remember the tables in which I filled out all the possible values, even those you couldn't observe. The assumption in classical physics is that those properties that you did not observe still have actual values. You just weren't able to see them. But if you make that assumption, then you're going to get Q is less than 2. Therefore, don't try to fill out the values for the properties you didn't measure. Don't imagine that those property values exist, but you didn't measure them. They didn't exist. The only thing that exists is the property that you actually measured, and that you chose which one to measure. Alice chooses to measure, this one or that one, and the one that she chooses not to measure doesn't exist. So it's not like arms and legs of a dancer, where you just choose to measure which one. So it's like the dancer has arms and legs, but if she chooses to measure the legs, she can observe it, and for example, she sees leg down. What about the arm? Well, the arm exists, but the property of the arm being up or down does not exist. So that's totally non-classical. It even sounds nonsensical. Well, it is nonsensical for dancers, but for photons, it's actually the way it works. Other examples down here, the path in an interferometer. Remember, we talked about a photon can take the upper path or the lower path, and then the quantum possibilities interfere. But remember, we also said if you observe which path it takes, the interference no longer occurs. So what that means is that you have to have a unitary process. You have to enclose the interferometer in a black box and not look inside it to try to figure out which path the photon is taking. In that case, the question which photon path was the correct path, that is a ill-posed question. It's a nonsense question because it has no answer. On to a Jamboard question. The Jamboard is in the chat window. You can click on that. The question is, how would we design our experiment to prevent hidden communication between the two sides of the experiment? So this is one of the possible loopholes. We've talked about it before. We want to have an experiment where average Q is greater than 2, as Henning just did. But we want to prove Henning's experiment so that we can get Q greater than 2, while at the same time ensuring that there could not have been communication between Henning's 2 detectors. And his detectors are very close together, right? They were just, 10 centimeters apart. So inside the detectors, or which is inside of his box, there could have been some unknown communication going on between them, which was rigging the system. How could we fix our experiment, redesign Henning's experiment so that that's not possible? Okay. Yep, nothing travels faster than the speed of light. And we certainly know that's true for physical objects, right? Because if you take a physical object and start accelerating it, it gains more and more mass because it gains more energy, and therefore it becomes harder and harder to accelerate. So you can never accelerate a physical object faster than the speed of light. But it's also a very fundamental part of relativity theory that nothing can travel faster than the speed of light, including information. And that's consistent with the idea of a laser pulse or a radio pulse, because those are electromagnetic waves and they do travel faster, they travel at the speed of light. And according to all the physics theory we have, both classical and quantum, nothing can travel faster than the speed of light. So if we put them far enough away that they couldn't communicate via light speed before the outcome is known, that's exactly right. So, but now it's not just the result is known, okay? It also means that Alice would have to flip a coin and decide on the analysis scheme, and then get the measurement, and all within a time duration, say, 1 second, that is shorter than the time it would take a signal to travel between Alice and Bob. So if it was 1 second, if you put Alice on the moon and Bob on the Earth, I think that would be sufficient for them to be isolated for at least 1 second, right? Because it takes light more than 1 second to reach the moon. In a laboratory on the Earth, what they do is they separate Alice and Bob's experiments by maybe 1 kilometer, which means the two sides of a city or the two ends of a very long building that might be 300 meters long. But then they have to do everything fast, like within nanoseconds, or at least microseconds. So Alice has to have an automated method of choosing measurement setting and making the measurement and recording that all within 1 microsecond. And it has to be done very randomly as well. And Bob has to have the same kind of setup. So great. So on page 2, I have shown exactly the answer that you just proposed. So I think of this setup as a fictitious information-proof wall. There's not really a physical wall there, but the time lag of the light speed for transmitting information effectively builds an information-proof wall between the two sides. So no matter what unknown conspiracy is going on, if we believe relativity theory, then we think we have been able to rule out the possibility that whatever conspirators are on this side, we rule out the possibility that they could communicate with other conspirators on this side. So that's nice. And that experiment has been done by 3 or 4, actually 4 or 5 different laboratories around the world, just in the past 3 years. Now here's another possible flaw or loophole. Based on the fact that typical photon detectors detect only about 80% of the photons hitting them. So, Henning had detectors that detect maybe 20% of the photons hitting them. The other photons that hit the detectors are simply not detected. Why would this be a separate problem for the experiment? Why could this possibly rule out that the experiment is telling us what we think it's telling us? Remember, each photon enters into the lab. So they come from the source, and a photon enters Alice's lab, and now it's in there. It can't communicate with Bob's lab and Bob's photon, but it might be able to do something conspiratorial when it gets near the polarizer and near the detector. And think outside the box. Don't limit yourself to known physics. This would be new physics if this kind of thing could happen. Imagine a photon is a little intelligent machine, and it has built inside of it the ability to do things and make decisions and choices and decide whether to be detected or not detected. How could it conspire? Okay, so right. So I wrote the one in the blue here because time is getting a bit long. And it's not that the photon could communicate with the other photon or with Alice or Bob. It doesn't, no, it doesn't communicate. We've already ruled out communication by putting the two laboratories far enough apart and doing the experiment quickly enough. But what could happen is what I said in the blue box, and this is not so obvious, I think. But each photon, if it had some decision-making ability, it could decide to be detected or not. It could self-select or self-deselect. And how it would do that, it would look at how its analyzer is set. So the two photons could have a conspiracy that they set up at the source when they were together. They said, well, I'll do this, you do that. And then once each photon gets to its analyzer, it looks at the analyzer and they see how did Alice set the analyzer? And then the photon decides, I'm going to be detected or I'm not going to be detected. It turns out that that is sufficient to create a conspiracy and to destroy the conclusions that we'd like to make about the experiment. Okay, so this one had to be fixed. So what people have done in the past 10 years, and I know some of these people at the laboratories in Boulder, Colorado, the National Institute for Standards and Technology, they've created detectors whose efficiency is 90, I forget exactly the number, but it's something like 99.8%. And it turns out that that is far higher than is even needed. If you had detectors of 90% or so, you can prove by statistics theory that that would be sufficient. So they've solved this problem recently, and this is not a problem. So we're perfectly confident that there could be no hidden mechanism of this type. Okay, so now I'm going to go back to Keynote, and I'm just going to summarize this one. No information can travel faster than light. Information, and then the detector one. Or it could be the detector that senses what its photon will do and conspires to generate a click. So it could either be the photon or it could be the detector, or they could conspire together. Okay. And like I said, these experiments were done in 2015, and they still observed Q equals 2.8, which is much greater than 2. So we've shown that experiments have eliminated these two loopholes, the communication loophole and the detector loophole. Well, is there another loophole? No, these are closed here. Yeah, see, this one is closed by the speed of light. So we already discussed that one. Okay. Here's a cartoon I made up of Alain Aspect. I showed him this a couple of years ago at a conference, and he just laughed. But what I've shown is that Alain here is under remote control by something. Some unknown aliens are out there controlling both Alain and Alice on the other experiment. And they actually don't have free will. They think they do. You think you have free will, but do you really? I mean, does your brain work like a computer? Does your brain operate according to the principles of physics? If it does, can you make free choices? Can a computer make free choices, or does a computer only make choices based on an algorithm? Do people only make choices based on an algorithm? So these are questions that are in some sense impossible to answer. Okay, turns out. So they took the people out of the equation, and they built fast random number generators to do the analyzer switching. So now there's no question about the people making free will choices. Now, how do you build a fast random number generator? Do you remember how that was done. I'm going to go to Jamboard. So everybody go back to Jamboard, and I'm going to put a new question in here. How can they make really good, truly random numbers to control the analyzer settings? Okay, there's our new question. In the Jamboard. Build a quantum computer. Well, we don't have quantum computers, so they didn't use that, but they used something a little bit similar to that. They can't use a regular computer because regular computers just follow algorithms. Right. Prepare a quantum state in a superposition of several states and measure it. That's right. Or even if you prepare a photon in a single state, like V polarized, and then you measure it in the dA basis, you'll get a random result. And if you remember, Henning actually did that experiment, and he demonstrated on his screen a bunch of zeros and ones that were being spit out at random. That's right. So that is essentially what they did in these labs. They had another setup, which was using quantum probabilities to generate these random numbers. So that sounds pretty good, right? But is that good enough? So Alice has this quantum random number generator sitting right next to her photon detector. And remember, the photon detector could have a conspiracy inside of it, which observes the incoming photon. Well, no, that's not true because we have high efficiency. So the detector cannot do anything. Detector must detect the photon. Okay. However, maybe the random number generator could observe the incoming photon somehow because it's inside the lab. It could look at the photon and somehow sense what its quantum state is, and then it could create its random number, not randomly, but according to a conspiracy rule. Right. How do we know that these are really random? See, it's like circular reasoning, because we're trying to do an experiment that tells us something about quantum physics, and then we're saying, oh yeah, these measurements these random number generators are really random, and they're built on quantum physics assumptions. So yeah, we can't just assume that, right? So if they weren't really random, and if they were conspiring with the incoming photon, it could still be a loophole. So now what did they do? Just like they had to separate Alice and Bob, what you have to do is you have to separate your random number generator from Alice, and also separate Bob's random number generator from Bob. And this gets a little bit subtle, I have to admit, actually, but let's go and look at it. Where's my keynote? There we are. So what did they do? They used random number generators that were 500 light years away from Alice and Bob. So Alice is in one lab on the Earth, Bob is a kilometer away, so they can't communicate with each other. Then they use photons coming from a star, or the photons created 500 years ago. and it travels here. It was created long before Alice and Bob even were born, right? So it's coming along. It has a quantum state, whatever it is, and then they put it into a HV analyzer and measures polarization. And the result of that measurement then automatically sets the angle of this crystal. They actually did this experiment. It's an amazing experiment. And Bob's lab has the same thing. Bob has a telescope, and a photon comes from a different star. This is supposed to be a completely different star on the other side of the sky. And it's emitting photons also about 500 years ago, completely far away from this Alice's star. And that star controls the angle of this crystal. So we really push things back. And in principle, you could push that back even more than 500 years. You could push it back billions of years. In principle, you know, people have detected radiation from the Big Bang. You put up a radio telescope and you can measure radio waves that were created in the Big Bang and are still bouncing around the universe and hitting Earth, and you can detect those. And you could use radio frequency photons from the Big Bang to set these analyzer crystals. So then you're pushing everything back as far as the Big Bang, which would mean that if there's a conspiracy that's controlling what Alice and Bob does, or Alice and Bob's apparatus does, it would have had to have been hatched during the Big Bang, before there were even atoms existing. So that seems pretty ludicrous, right? So the normal conclusion that everybody makes from all this is that indeed the Bell inequalities are valid. There's no conspiracy, there's no rigging, and the fact that Q is greater than 2 means there's something wrong with the assumptions that went into the derivation of the Bell inequality. Okay, I hope you followed all that logic. So what could be wrong with the assumptions that led to us deriving the Bell inequality? Okay, these are called Bell test experiments. And strictly speaking, what all these experiments prove, and proves beyond any rational doubt, that the combination of locality and realism and measurement independent cannot exist, or I should say does not exist in our universe. We don't know why, but this is just the universe that we live in. So remember, locality or local causality means it's simply the claim. It's like a philosophical statement. We claim, like Aristotle might say this, okay, I claim one of my principles. No influence can travel faster than the speed of light. So two distant objects cannot influence each other, namely they cannot communicate or affect each other in any way within a short time period, okay? So the second assumption that Aristotle might have made is realism. I think he probably would have said this, that all objects and entities have pre-existing inherent properties or instructions for measurement outcomes. Like Alice's arm is either up or down, no doubt about that, whether you look at it or not. It's independent of other entities like Bob's leg, you know, and it's also regardless of how or if these things are measured. So it doesn't matter if you observe it or not, they do have pre-existing inherent properties or instructions. The third assumption that Aristotle might have made is that people have free will. And that we just showed that if you don't trust that statement, you can use quantum generators that generate random numbers as far back as the Big Bang. So we believe that as far as anything can be random and independent, those two measurement settings can be so. Okay, so those are Aristotle's three philosophical claims. We call it a worldview. And it's the worldview that almost everybody who knows anything about classical physics should believe, right? I mean, which one of those don't you truly believe in your own heart? Yeah, okay. Well, can we conclude that one of these must be wrong? At least one? Yes. The experiments have now proven that at least one or more of these is simply false. Now, there's no way to know at this point which one of these is false. And very smart people would pick different ones of these three to claim is false. I think earlier somebody mentioned wormholes. So yeah, there could be wormholes. There could be influences that travel through wormholes and would appear to go faster than the speed of light. There's no evidence for that. There's not even a good theory for that. Free will. People could claim, yeah, these correlations were built back in the Big Bang, and there's nothing we can do about it. And you don't really have free will, you just have the illusion of free will. In fact, if you Google free will, you'll see a whole bunch of articles and books that make the case that people don't really have free will. We think we do, but these arguments say that we're just like a fancy computer. Computers can make decisions, right? They make decisions all the time. You know, automated self-driving car driving down the road, car stops in front of it, it makes the decision to stop. That's a decision, and they use artificial intelligence to do that. So maybe humans are the same way. Okay, realism. Well, we know that baseballs and arms and legs are real, and they have real properties, but you can't really say that about photons and electrons. So maybe that's the one that's false. So what should we do?
Dr. Raymer,
Yes.
before you continue, a student had a question about your previous slide.
Okay, I can scan back to that. This one?
Yes. They want to know why the Q value is always 2.8.
Oh, that's a good question. Very sensible question. It turns out that nobody has ever observed a Q value greater than 2.8. Remember, I showed you can rig it up and get 4, but that would be only true if you had rigging. And we've just shown that we're very confident we can get rid of all the rigging and conspiracies. So so it's not necessarily possible you can get up to 4, but we know we can get greater than 2 because Henning just showed that. So why can we not get bigger than 2.8? That's actually not known. It's really not known why we never get greater than 2.8, but no experiment has ever shown greater than 2.8. So that's a very important fact. Now, if you use quantum theory to predict what is the greatest possible Q value you could ever get in any experiment, you can calculate that very straightforwardly. The answer is 2.8. So quantum theory correctly predicts the maximum possible value of Q, and it also clearly predicts that Q can be greater than 2, and it correctly predicts that you'll never see greater than 2.8. I actually have some slides that prove that. Well, no, not prove that. I do have some slides that calculate Q and show that it is equal to 2.8 using quantum theory. It's a very hard math problem to prove that you can never exceed 2.8. So thank you for that question. So what can we do? We can fall back on the following position. You can make up all kind of crazy excuses for why Q is observed to be greater than 2. And these are getting more and more crazy, right? Or you can do something very simple. You can say, I have a theory. It's called quantum physics. It's been developed for 100 years. It works to explain every possible experiment that's ever been done. It's a really, really good theory. If I apply to this experiment in which I assume there's no hidden crazy conspiracies, quantum theory predicts exactly the right correlations. So at least we have a theory that predicts the correlations correctly. That's really great. And we can use that theory to then turn around and build quantum computers and other things. Now, it still doesn't tell us why quantum theory is correct. It doesn't tell us what's going on, because quantum theory is just a model. And all physics theories are just models. But the good news is we have a theory that works perfectly, so just don't worry about it. But philosophers like to worry, so we'll keep worrying. So here's a possible philosophical viewpoint you could have. You could say, let's say we really like causal locality, because we really don't believe in wormholes, and we really do believe in relativity. And that tells us that there can never be any influence between Alice and Bob's lab, and no communication. Let's also say we want to retain free will, because otherwise, as I say here, life is very different than we think it is. I would bet that almost all of you think you have free will, and would really not be willing to give up that assumption. So relativity and free will are valid in this particular worldview that you could construct. So this means we must reject realism, because it was one of the basis of our calculations. When we created those tables, in order to prove that Q could not be greater than 2, we had to assume that the values that were never measured, or the properties that were never measured, nevertheless did have definite values. We just did not observe them. That's called realism. And if you give up realism, then you say, no, those properties that were never measured never even existed. But that's weird, because if Alice then chooses to measure one property or the other, she can decide what elements of reality exist. That's almost like a godlike action. She's creating aspects of reality as she goes. In fact, Henning was doing that, and you saw him doing. Henning was creating reality. So if you, I'm going to overstate the case here to make it sound funny, but if you believe in relativity, and if you believe you have free will, then you have to believe that Henning was just creating reality. But so what would it mean to have a theory like this? Okay, so just going quickly because time is running out. One thing you might say is that these non-local correlations don't require any physical mechanism. In other words, there's no conspiracy, there's no hidden activities going on that we're not aware of. In other words, not all correlations are necessarily caused by causes. They just exist. And that's just the world, the way the world is. It's the way the world was given to us when it was created. They're just there in the fabric of nature. And amazingly, Henning could reveal those by his experiment. So we didn't have to have a mechanism. This might be fairly close to a lot of physicists thinking right now. We know there's no physical, well, we believe there's no physical mechanism because that would require some new physics that we're not aware of, and it would seem to be really outlandish type of physics. So that could mean that there's simply no causes for these things. It just happens. And we observe it happening. We use quantum mechanics to predict the statistics for which it will happen. That theory works very well, and that's it, we're done. That might be the way it is. But it's still a very strange thing. So yeah. So the mathematics of quantum theory that we'll discuss on Monday is called quantum entanglement. And I say it's to the rescue because it's a beautiful mathematical structure. It perfectly describes all the Bell inequality and all the correlations that you observe in the experiments. And it allows quantum computers to operate. It allows quantum teleportation and other things, which do work. We have observed quantum teleportation. So again, we believe quantum physics is correct. So even though we don't have the deepest philosophical understanding of what's really going on, we have a fantastic theory that works really, really well. And so on a parting comment here, you should read the reading that's assigned for Monday. And I introduced this notation here, new notation, okay? The state of a pair of particles. Alice's photon is this one on the left, and Bob's photon is this one on the right. So this and symbol means and. It means that Alice's photon is vertically polarized, or it's in a vertical quantum state, and Bob's photon is in the horizontal quantum state. But now there's another possibility that Alice's photon could be in the -h state, and Bob's photon could be in the V state. So those are two distinct quantum states of the pair of photons. And those are both valid quantum states, I'm sure you would agree. So now the very, very cool thing is you can make a quantum superposition with the plus sign. It's a superposition of these two possibilities with these other two possibilities. That's an entangled state. And that little equation right there is so non-classical and so weird that Einstein and Schrodinger really didn't like it. They thought there was something crazy about it. But now we know it's true, and if it weren't true, we couldn't build quantum computers. So you can think of these as qubits. This is Alice's qubit, and that's Bob's qubit. So this could be 1, 0, right? It's like a little memory register. You put data into the memory register. You have two little cells, and you put a 1 into the first cell and a 0 into the second cell. But that state could be quantum superposed with this other state where there's a 1, well, the opposite way around. That's 1, 0, this is 0, 1. So it means you have a register of two cells which can encode two different combinations of data in a quantum superposition state. And this is what you need in order to model the Bell experiments. And like I say, it works perfectly. So I'll see you on Monday, and have a nice weekend.